So today, guys, we'll be finding out the proofs for the various derivatives of trigonomic functions. So for now, I'm just going to quickly write out the 6 basic ones, which you should already know, but probably don't know maybe how to prove each one in case you ever were to forget them. Now, I kind of wrote them out in a way where they're kind of paired up and next to each other, because as you can see, they're pretty similar aside from a sign change and a sort of opposite of their respective trig. So just by going over 4 of these, you should be able to define the remaining ones going through the same process and steps. So today, that's why I'm just going to prove these 4 right here. And you should be able to prove the rest on your own. Now, before I begin, there are 3 basic things you do have to know from pre-calculus in the beginning of derivatives to actually do this. And the first one will obviously be the definition of a derivative, which if you don't know how to prove that, you can go refer back to my first video that I made on defining the derivative and understanding it. But also you do have to know these basic common limits that I won't be proving here, but they're fairly easy to define. You can probably find it online. But it's sine x over x equals 1, and 1 minus cosine x equals 0. And if you rewrote the 1 minus cosine x over x, that's the same as also saying cosine x minus 1 over x is also equal to 0. And you could show this by just factoring out a negative 1. And then taking the limit, you're left with negative 1 times 0, which is still 0. So they're both the same thing. We mainly need the second one here, but usually when people define it, they tend to show it the first way with 1 minus cosine x. And lastly, you do have to remember from pre-calculus these sort of trig expansions, like if you have sine a plus b, that's equal to sine a cosine b plus cosine a sine b. And same goes for the cosine, where cosine a plus b equates to cosine a cosine b minus sine a and sine b. Now these you should remember from pre-calculus, but in reality, all 3 of these are just to help us find out the derivative of sine and cosine. But in reality, tan, secant, cotan, cosecant are all defined from the proof of sine and cosine's derivatives. So to begin, I'm just going to rewrite that dy dx of sine x is cosine x and the definition over here. And so we're just going to go through the motion of plugging into the definition. So wherever we see x, we plug in x plus h. So sine x plus h, then minus sine x, all divided by h, and can't forget the limit. And then next, you see over here the sine x plus h. That's similar to the sine a plus b expansion I was talking about earlier. So we're just going to go through that, where a is x and b is h. So the limit h tends to 0, it would be sine x cosine h plus cosine x sine h minus sine x, all divided by h. Now from this first and last term, we're going to factor out a sine x, and you'll see why we do that, because it'll give us those special common limits. So if we were to factor out the sine x, we're left with cosine h minus 1 plus cosine x sine h, and all that divided by h. And then finally, we're going to split up the denominator between the 2 terms, so we're left with sine x times cosine h minus 1 over h plus cosine x times sine h over h. And then if we were to take the limits of these two common limits right here, we know that this evaluates to 0 and the other evaluates to 1. And we can go ahead and get rid of that limit h tends to 0 because we've eliminated all our h's. So that means sine x times 0 plus cosine x times 1. Well, that just leaves 0. 0 plus cosine x, which evaluates left to cosine x. Derivative of sine x is equal to cosine x. Now, to kind of show you how this works with the opposite, let me just move this over here so we could solve the derivative of cosine x, which is negative sine x. So it's the exact same motion. We're going to write the limit of h to 0, go through the motion of the definition, and then we're going to expand it by the cosine expansion over there. So cosine x cosine h minus sine x sine h minus cosine x all divided by h. Then we do the same thing where we factor out a cosine x from the first and third term. So we're left with cosine h minus 1 minus sine x sine h divided by h. Then we're going to do the same thing with the denominator separation. So we're left with cosine x times cosine h, cosine h minus 1 all divided by h minus sine x times sine h divided by h. Same thing with the common trig limit. So we know the first part evaluates to 0, second part evaluates to 1. So then we can get rid of that limit, h tends to 0, and we're left with cosine x times 0 minus sine x times 1. Well, that's going to evaluate to 0. And then we're left with the prime of cosine x equals negative sine x. So now that we've solved the derivative of sine and cosine, finding the derivative of the remaining just requires knowing the quotient rule. So the derivative of u divided by v would be u prime v minus u v prime all divided by v squared. And you should know this fundamental property of derivatives. And we're going to apply this to finding the derivative of tan, which is secant square x. Now the reason we do this is because we know that tan x is the same as saying sine x divided by cosine x. So we can rewrite this as the derivative of sine x divided by cosine x is equal to secant square x. And now we're going to go through the motion of the quotient rule. So we know sine x is our u and cosine x is our v. And if we go through the motion, we're left with the derivative of sine is cosine x times cosine x minus sine x times negative sine x, because that's the derivative of cosine, all divided by v squared, which is cosine square x. And now if you were to simplify this, we're left with cosine square x, negative times negative is positive, plus sine squared x, all divided by cosine square x. And then this is a Pythagorean identity, which evaluates to 1. So we're left with 1 over cosine square x, which you could flip back up to secant square x. And that's pretty much it. The prime of tan x, or derivative, is secant square x. And like I said, the same thing goes with sort of partner or opposite with cotan x, except we know that is cosine x over sine x, which is kind of flipped. And therefore, when we go through the same process, we'll find that it'll actually end up being negative cosecant square x, because over here, instead of 1 over cosine square x, it would end up as negative 1 over sine square x. Now lastly, finding the derivative of secant x and proving it's secant x tan x. Now we can again rewrite this, that secant x is 1 over cosine x. So instead we could do 1 over cosine x. Now we could technically flip this up to cosine negative 1 to the negative first power into chain rule, but I'm going to stick to the quotient rule. So yeah, 1 is our u, cosine x is our v. So we're left with derivative of 1 is 0 times cosine x minus 1 times negative sine x, all divided by cosine square x again. That cancels out. So we're left with sine x over cosine square x. And that's the same, we could split up into sine x over cosine x times 1 over cosine x. Now we know sine over cosine is tan x, and we could flip that back up into secant x. And there we have it. Derivative of secant x is tan x, secant x, or secant x tan x, same thing, commutative property, whatever. And same thing again with its partner, cosecant x. It's the same thing, 1 over sine x. So if we went through the motion, we'd end up with negative cosine over sine, which would become a negative cotan, and 1 over sine would become cosecant. So the derivative would end up being negative cosecant x times cotan x. And again, you could go through the motion yourself and kind of prove it on your own, but it's the same thing. And yeah, that's pretty much it.